Your book describes sound as a disturbance of matter that moves outward from its source. And that's a pretty good definition of sound because it helps us figure out that sound can travel in, more than just air. It can travel through substances as well, any substance, but it does need a substance to travel through, unlike light. So it is a wave that needs a substance to travel through, or a medium to travel through would be a better way to put it. Sound is a type of wave called a longitudinal wave as opposed to a transverse wave. That means that what's creating the sound is moving back and forth, and the sound waves themselves are made up of particles that are also moving back and forth. So a longitudinal wave, by definition, is that the matter that's moving, that makes up the wave, is moving in a direction that is parallel to what is creating the wave itself. So if we're taking something and shaking it back and forth like this, and then the particles are also moving back and forth like that, then that's a longitudinal wave. So sound looks a little something like this. We can picture sound maybe being created on a string. And it would look something like this. And so what we have is the string here moving back and forth like this as it's being played by whatever instrument it's attached to. And then what that string does is it causes these areas in the wave to be compressed, right? It kind of pushes all the air particles near it together really fast all of a sudden. It causes them to compress. And then on the opposite side, it's sort of pulling air molecules away just a little bit, and so it creates this area of really low pressure, which we call rarefaction. So a sound wave is made up of compression, which you can think of as maybe the peak of the wave, and rarefaction as the trough of the wave, so kind of the low point in the wave and the high point in the wave. And that's how sound is going to work. It's these areas of varying pressure of compression and rarefaction that actually then sort of travel and continue on. Right? This area of compression is air molecules compress, they bump into the ones next to them, compressing them, and so on and so forth. And then as they hit each other, they sort of rebound and recoil and create these areas of rarefaction. So that's how it gets transmitted, say, from our string to your ear. So let's look at just kind of a general wave in a little bit of detail here. And it's almost easier to look at a transverse wave for this. So that's what we'll draw. And you can just picture, this area here being the compression part of the wave, this area down here being the rarefaction, and we're just graphing pressure, right? High pressures, low pressures, high pressures, low pressures, that sort of thing. So it works for our sound waves as well. A couple very important definitions here. We have wavelength of a wave is the distance between two common points. Usually we'll do, say, peak of the wave to peak of the wave, or trough to trough. And that would be the wavelength of our wave. We use the Greek letter lambda for the abbreviation of that. The amplitude of the wave, right? Amplitude, remember, was our maximum displacement from equilibrium. So we could have our amplitude there. And we can also have a frequency and period of our wave, which are just like frequency and period in simple harmonic motion, right? Like number of cycles per second. One other important component to measure of a wave is the velocity for a wave, right? How fast that wave is traveling. And there's a very simple equation that we can use using some of the things we talked about to find it. Velocity of a wave is equal to the wave's frequency times its wavelength. If we think about units here just for a second, remember frequency is 1 over seconds. Wavelength, because it's a distance, right? It's like how far from one peak to another, is in meters. Put those together and you get meters per second, which we're used to for velocity. So the frequency of wave, number of cycles we complete every second, times the distance for basically a cycle, is how fast our wave is going. Now the speed of sound is also dependent on what medium you're in. So kind of an interesting thing here, and this is an important point. Frequency and wavelength do not determine the speed. The speed and the frequency determine the wavelength, and that's the way the physical relationship works here. It's not nice and straightforward like this, right? You can't change the wavelength and change the speed. Because sound travels through a medium, it's the medium itself that determines how fast the sound is traveling. Right? If we have a bunch of particles that are densely packed together like this, it might be harder for them to move back and forth and transmit that sound. Whereas things that are spread apart have a little bit more room for that kind of back and forth movement that we talked about, and so it might be easier for them to emit sound. And that's kind of how it works in gases. If we want to actually calculate the speed of sound in air at any given temperature, there's an equation that we can use to do that. How we do that is we take the value 331 meters per second, which is kind of our standard value at sea level, and we times that by the square root of our temperature over 273 Kelvin. So we want our temperatures here to be in Kelvin, so plus 273 degrees if we're talking about our Celsius scale. Divide by 273, take the square root of that, and times 331 meters per second. And that would give us the speed of sound in air at given different temperatures. Temperature matters because temperature is going to affect how densely packed these things are, right? Cold air is going to look more like this, hot air more like this, and so that's going to affect how fast it actually travels through the air. So this equation will be useful when we have temperatures that aren't what we would consider kind of a standard temperature. So revisit one point here that I think is important to remember, and that is that sound, the speed of sound, is independent of the frequency. In other words, frequency doesn't affect how fast that sound travels. Frequency has to do with sort of what's generating the sound, how quickly is it moving back and forth, which is good because if you were sitting at a concert, let's say the stage is over here and the sound is moving that direction, and you're over here standing and listening to the concert, if velocity was affected by frequency, then that would mean that high frequency sounds might travel faster than low frequencies. So that means high frequency sounds would actually get to your ear before the low frequency sounds that are supposed to sort of be associated with it for whatever bit of music you're listening to. And so then it would sound really weird that those, things wouldn't match up, and it would be different for every person along the way because it would take a different amount of time for each thing to get there. So the fact that they do all travel at the same all frequencies travel at the same speed in a given medium is a good thing for us and allows us to do things like listen to a concert from far away. One more interesting situation to look at, let's kind of think about some water here and our source of sound kind of coming towards our water. So our speaker up there, our sound moving this direction into the water. What I want to know is what happens to frequency and wavelength as we enter the water. Well, if we change medium, frequency, turns out, stays the same. Okay, and this is because frequency is sort of what's driving the sound, right? Over here there's a speaker moving back and forth at some rate, and that same rate is being translated into the air, and then when those air molecules come in contact with the water molecules, it's going to cause them to move back and forth at the same rate. And how quickly those molecules are moving back and forth is frequency. So because those molecules are bumping into each other at the same rate and causing them to move back and forth at the same rate, when we change mediums, let's say from air to water, our frequency stays the same. But because our velocity is going to change, that is going to change something, which is our wavelength. So when we change mediums, we're changing our velocity, which changes our wavelength, but not our frequency, because our frequency is sort of independent. Our frequency depends on what's creating the sound, what's driving those sound waves.